Hello ladies and gentlemen, good to see you again. This is the 9th lecture for GGS 300 and today we're going to be focusing on two sample tests. So where are we at currently? So you should all now have submitted assignment 6 and this week it's already been set. Assignment 7 has been released and that should be due on October the 30th. Some of you have reached out to me saying that you still aren't understanding a couple of concepts. Good for you. Make sure you make use of my time. I'm happy to Zoom with you to help you try and understand any parts that you're still not clear on. And it's definitely good for us to try and clear this up now before we move into the final few lectures this term. So please make sure that you're reaching out to me if you've got any further queries. So what are we doing today? Well, we're going to be introducing inferential tests that focus on two samples, okay? So what do we mean by that? So we focused in the first part of the lecture series on descriptive statistics, so mainly on this side of the screen over here. And then on the last couple of lectures, and definitely for the remaining part of the term, we're going to be focusing on those inferential tests, which allow us to formulate different hypotheses and then quantitatively determine whether the data that we have supports the rejection of the null hypothesis, or whether we don't have enough information to reject that null hypothesis. So this is a more advanced form of statistical testing and trying to make statements about how the world works, essentially different levels of confidence. That's what this is all about. Before I progress, I just wanted to introduce this concept to you that there are these different types of statistical flowcharts which can help you determine which tests you might want to use, and this is by far by no means comprehensive, this particular one that I'm showing you here, but it's just to give you a gist that there are all these different tests. But then some of them are specifically used for different types of data or for different distributions of data, and that can be incredibly confusing. And I know because I've been there when I first started learning this. But the beauty of these types of flowcharts to help you determine which test you need is that it demonstrates that there is a boundary to all of these tests. There's only a set number of them, at least for the main types. And therefore, while this may look confusing and quite daunting at first, in reality, you would actually be able to work out which test you would need from this if you knew the different dimensions of your data, okay? So for example, later in the term, we'll be focusing on discrete and categorical data. Today, we're focusing still on continuous like we were last week. We're focusing on differences. And for many of the tests today, we're focusing on the difference of means. And we've got today multiple treatment groups. So let's say there's two groups. Then the question is whether we need a parametric test, so a test for normally distributed data that's continuous, or maybe we don't have normally distributed data. Maybe we need a non-parametric test. In which case, then it leads us to these two different types of tests that we're going to be covering in today's lecture. So the unpaired t-test, and then also the Mann, Whitney, U, and Wilcoxon ranked sum tests. And we're going to be doing that in different ways, both with independent data samples and also with paired data samples, so that the same entity is being surveyed perhaps at different points of time. Okay, so this just gives you a general overview that if you're trying to work out which statistical test you might need to use, one of these charts might be useful to you, and there's quite a few on the internet. There isn't a comprehensive one yet for the book that we're using, so that might be quite a good dissertation topic if you wanted to try and create one of those. Maybe a methods-focused research dissertation which tries to track out all of the different spatial data analytical methods that could be used. I think that would be a great thing to do. Or you may just want to work out how to analyze the data that you've collected for your dissertation thesis. Okay, so without further ado, let's move on. Let's focus on the concepts of two sample tests. So you'll remember in the last lecture we focused mainly on one sample. However, there are many examples where you might have two different samples. So we could test if two cities have different crime rates. We could examine if forests have different mean tree heights or different growth properties. We might want to test before or after a particular intervention. So for example, perhaps we introduced a new type of fertilizer on a farm and we wanted to test how much production there was in one year compared to another year after we'd introduced that new type of fertilizer. Or the example that I'm going to keep coming back to today is testing if there's been house price changes after a major economic disruption. So maybe what we did was we went out and we sampled houses in Fairfax City, and essentially we're interested in what the price is going to be, say at the start of 2020 prior to COVID, and then perhaps at the start of 2021. So after COVID's been prevalent for 9-10 months in the United States, and whether that might have an impact on the house price. So these are examples where we may have two different samples, and they can be independent or they can be from the same entities, and we're going to cover this today. Essentially, the samples are significantly different. If the samples are significantly different, then we can conclude that the samples are drawn from significantly different populations. But that means that if there is no statistical significance between the samples, then basically we can conclude that they're drawn from the same population. And that's essentially the logic that we're going to be using to understand the use of these tests. Okay. Data types. So for one sample tests, we had different tests for different types of statistics in the previous lecture. We will be focusing mainly on means today, but we will also do one or two proportional tests. So we did some of those in the previous lectures just for single samples. The actual data type of the variable that we use does have an impact on our choice of test. So for example, if you've got interval or ratio continuous data, then parametric tests are appropriate if all of the assumptions are being met. But if we had ordinal data, then a non-parametric version of that test would be more appropriate. And there's no easy way to get around understanding this. I'm afraid you're just going to need to learn that parametric tests are for normally distributed data which are continuous. Non-parametric tests are for non-normally distributed data where potentially you've got ordinal data rather than continuous data. And you just need to learn that in rote form, unfortunately, so that when you're tested on it, you know the difference. And I think that there's a lot of information for you to pick up this term, but a lot of it is kind of combination of qualitative and quantitative. So we're expecting you to be able to qualitatively understand how different tests are carried out and the differences between them, and we expect you to be able to run some code and manually work out some of those tests to get the right quantitative answer. There are thousands of different statistical tests. You don't need to learn all of them. The point of this course is just to make sure that you have that basic understanding about some of those key principles, whether it's sampling or probability or the central limit theorem, so that if you choose to go on and do further work, then you've got a good background in this subject. Or if you're presented with statistical information once you've entered the workforce, you're able to think critically about those different factors which affect the results in statistical analyses, which is really important. And they could be assumptions, for example, as we're picking up here. So you're going to need to learn this, unfortunately. Make sure you read the book, make sure you go over the material and the lecture here, make sure that you do the lab work, and I think you'll be very well set up then to excel within this particular course of GGS 300. Independence. Now, this is something that we're going to come back to many times. So this is a qualifier for which affects which test you are going to choose. When we move on to regression later in the term, independence is going to be something which we come back to. It's a perennial issue. And this really relates to the data samples that you have. So, for example, an independent two-sample version of data would be when you sample something and then you sample it again, the fact that the samples are essentially unrelated. So if I told you I wanted you to go off and I wanted you to sample Fairfax and Richmond, and I wanted you to sample the house prices in those two places, they would be independent samples because they're different locations. And that then contrasts with dependent samples where you have matched pairs. So this could be where you basically have the same subjects, so the same data entities that you're sampling, but what you're doing is you're getting a before and an after snapshot, for example. So maybe I told you that I wanted you to go off and sample house prices in Fairfax and Richmond, and I wanted you to sample them before COVID and after COVID. Because they're not independent samples, you're going to be sampling Fairfax twice and Richmond twice. It's going to affect the statistical test that you then need to use. You need to use a statistical test which recognises the fact that these samples aren't independent, and therefore that there are potentially correlated errors that need to be accounted for. You need to make sure that you're comparing apples with apples when you're actually carrying out your statistical tests. So this is important, and we'll be going over tests today that focus both on independent samples, but then also on dependent samples. Okay. And just a couple of points then before we progress. There is only one two-sample test of proportions that we're going to use, so we're going to be covering this also within the lab today. We're going to go over one proportional test. And then you'll also remember from the last lecture, we focused both on hypothesis testing using the kind of formalized 6-step method, but then we also covered the p-value testing approach. Okay, so let me just present you with that information from last week. So we went over that formalized classical hypothesis testing approach where we basically state the null and alternative hypothesis. We select the appropriate statistical test. We select the level of significance, so the alpha value that we want to have. We then delineate the regions of rejection and non-rejection of the null hypothesis within the distribution. So remember, we had to find the lower bound and the upper bound if it's a two-tailed test. Or if we think it's directional, we'll have to find just the lower or the upper bound. And we need to find that bound in relation to the number of standard deviations away from the mean, so that we can be potentially 95% certain that the result hasn't just occurred by chance, if we want to actually reject the null hypothesis and accept the alternative hypothesis. Okay, so I hope that those 6 steps are familiar to you now. I think the key point is that you don't have to go through all of those 6 steps. Actually, a lot of the time you can just use the p-value that you're able to calculate, and that will give you an indication as to whether the mean that you have, for example, is sufficiently far away from the population mean for you to confidently say that it's significantly different from the population. Okay, so this is going to be a key concept. If you still don't understand this, relook at the materials that we've covered, particularly from the book. Reach out to me if you're still stuck, and we'll be able to cover it quickly in a one-on-one session. So let's get into the tests now. Let's focus on 2 independent sample tests first. So these tests are designed to check if 2 samples independently taken have significant differences between them. And often these could be independent geographic samples, as I've already mentioned. So perhaps we're looking at different average house price values in different locations. Perhaps we're sampling geophysical metrics from different places, potentially phosphorus load between 2 different lakes if you're focusing on a physical geographic topic. And essentially we have these different parametric tests and non-parametric tests. So we have the 2-sample difference of means test, which is one of the parametric approaches when you're using mean values, or you've got the 2-sample difference of proportions test when you're using a proportional value. In terms of non-parametric tests, we've got the Wilcoxon rank sum W, and this is essentially quite similar to the Mann-Whitney U test that we have mentioned already in this lecture, which is mentioned also within the book, but today we're just going to be focusing on the Wilcoxon approach because it's easier to calculate essentially. So what happens in the 2-sample difference of means test? Well, we're comparing the mean of 2 independent samples for difference. We have a set of assumptions. You remember from the previous lecture I said you need to make sure that what you're doing adheres to the assumptions that are required for the test, otherwise you're just producing junk results, okay? So you may have heard of garbage in, garbage out. That essentially means if you are putting, if you're doing a calculation, if your underlying data is bad, or if you're making bad statistical choices as for the method which you're choosing, there's no statistical or methodological approach for correcting for those errors. You're just going to produce junk results. It's going to be garbage in, garbage out. And that's really important. You need to kind of remember this. And what's important in your dissertation topics, for example, or when you start doing independent research, is that your method is strong. And I always remember someone telling me this when I was doing my thesis for my PhD. The examiners or people reviewing your work can disagree with the conclusions that you reach, but providing your methods are strong, rigorous, and robust, you've chosen the correct statistical methods, then they aren't able to necessarily criticize the method, and therefore, like you're in a strong place basically. If you don't do that and someone's highly skeptical of the method that you've used, or you haven't adhered to the correct assumptions, then you're in a really poor place, because the last thing you want is someone basically saying that all of your results are wrong because you used the wrong statistical test or because you didn't adhere to the correct assumptions. So when we present these tests, and also when they're presented in the book that you're following, there will always be these requirement boxes, and it basically just says, in this case, we need to have 2 independent random samples. The populations need to be normally distributed, so they need to have a bell-shaped curve distribution, the Gaussian curve, as it's been called before, after the person who first hypothesized that distribution. And also, it needs to be interval and ratio data that you're using this particular test for. So make sure you do consider these. It's obviously going to be important when you do your coursework this term and the exam, but also as you move forward to using more sophisticated tests. So what do we think of in terms of the different hypotheses? Well, hopefully now you've got a grasp of this because we've been over this before. So essentially, for the null hypothesis, essentially we would be saying that the mean for sample 1 and 2 would be broadly the same, and that they would essentially be the same as the population potentially. Whereas for the alternative hypothesis, you would be saying that the mean for the sample 1 and sample 2 are significantly different. We're just not saying which direction we think that is. So it could be that one's larger or one's smaller, but therefore this is a two-tailed test. We're saying that the effect, the magnitude of the effect, could be either large, so in the upper tail of the distribution, or small, much smaller, so in the lower part of the distribution, of the tail distribution. Okay, or we could say that the alternative hypothesis is basically directional. So for this first example here where my mouse is, we're essentially saying that the sample, the mean for sample 1 is significantly lower than sample 2, or in the other case, the mean for sample 1 is significantly higher than sample 2. So I hope that that's clear to you now. The null hypothesis and the alternative hypotheses that we state are complementary, so depending on where you set your alpha value, your significance value, you end up either having not enough evidence to reject the null hypothesis, or you have enough evidence at your chosen significance level to reject the null hypothesis. And the test statistics, so what are we trying to get at here? Well, it depends on the number of samples that you have. So Z being for the normal distribution, or if we don't have enough data samples, we might use the T distribution. But essentially, we're trying to find Z or T. Okay, and I think just one note before we get into the math. There are a variety of different ways in order to estimate this. So today we're going to be using the separate variance estimate, and you'll recognize this within the book. They also go over the pooled variance estimate, but we're not going to be getting into this in this particular lecture today. So we're just going to focus on the SVE. So how do we calculate that test statistic for this particular approach? Well, we want to find Z or T here. And the way that we do that is we subtract the mean of the samples from each other as the numerator, and we divide it by the standard error of the difference between the means. Okay? So I think that the numerator should be fairly straightforward for calculating. I hope that you know how to do that now. But for the denominator here, for the standard error of the difference between the means, we're going to need to use this estimator just down here. So essentially what we need to do is we need to take the square root of the sample standard deviation squared divided by the number of entities within the sample, and then we need to add these together. And then when you eventually get that, you're able to work out this particular calculation. So what this is doing essentially is it's accounting for the level of difference that we would expect to have by chance by taking random samples. So it's the standard error of the difference. I hope that that's not too complicated. I appreciate showing math equations might not be something which all of you are 100% confident with yet, and they are going to get slightly more complicated as we move through the term. Even some of the ones today may be a little bit more complicated. But I think the key point is you just need to be comfortable with recognizing that, you know, we have these Greek letters where we need to make sure we put the right numbers into those slots within the equation. What we have here is just basically the relationship, and we need to work out how to do that manually, so that then we're able to compare it with the automated tests that are generated through R. So if you're still stuck on any of that, please do reach out. So what's the test actually doing? Well, in summary, we're dividing the magnitude of the actual or observed difference in the sampling means, so this numerator up here, x bar 1 minus x bar 2, and we're dividing it by the magnitude of the expected difference in the sampling means, so it's this denominator down here. And basically we get a z or a t test statistic, and if the difference between the samples is large, then the test statistic will be large, and if the test statistic is of a certain size, that would indicate that there's potentially significant difference between the two samples that we've drawn, and that they potentially come from different populations. So let's go over an example of this. This is an example based on the one provided by McGrew et al. In the book. So if you go to page 161, then there's an overview of that. And you'll be able to look at this in tandem with this particular lecture example. So the question is, does the involvement of females in the labour force vary by economic level of different countries? So we have more developed countries over here on the left-hand side, and we have less developed countries over here on the right-hand side. And we have different sample sizes, so n, we have different means, we have different standard deviations, so the s, and we have different variances, so the s squared, and that's these four different numbers essentially that we get. So let's work through the calculations for these particular numbers. Well, first we need to define the hypothesis. So the null hypothesis is that there's no difference between these samples, okay? So the level of labour force participation by females is the same in both developed and less developed economies. The alternative hypothesis is that there's a significant difference between the means of these two different samples. In this case, as they're independent and they are using means, we're going to use this test that we've just covered, so the two sample differences of means. And we're going to try to calculate the test statistic, because you'll have noticed that we only have 15 samples in this one particular grouping of developed countries, and that's not over the metric of about 30 that we were hoping for in order to use the normal distribution. So we're going to use the t distribution here, which means we end up with the t statistic. So then we need to basically work through the math, and this looks, you know, big and really scary, but let's just go through it one at a time. So you'll remember that this equation here where my mouse is, this is the main equation for calculating the t statistic. So we have the difference between the samples, x bar 1 minus x bar 2, and we have the standard error of the difference between the means. And when we basically put the numbers in, we're able to calculate that it's about 0.44 essentially. And to do that, we first need to calculate also the denominator. So using the SVE approach, which is down here, this is how we calculate the 3.18 metric that goes in here as the denominator. And then this is the two two means of the samples that we have. Okay, so hopefully you can see 52.6 and 51.2 just here. And that allows us, when we've got those numbers, to calculate the t statistic. And essentially, when you look at the t statistic, then so it's 0.44. That equates to a p-value of about 0.65, which isn't significant at the 95% significance level that we're interested in. It doesn't give us a p-value below 0.05. So we basically don't have enough evidence to reject the null hypothesis. Okay. Now, I appreciate that that looks complicated, so what I've actually done, if you look down here in the left-hand side, is I've just tapped out in an Excel spreadsheet the data for the two different samples. So here's the data on the left for the more developed countries and the data on the right for the less developed countries. So it should mirror what you see here. And then I've calculated the SVE, so that's the denominator here. 3.18 based on this equation here, so we're taking the square root of these sums, so it's this calculation here, and then we calculate the t statistic by taking the two means from the samples and dividing it by the SVE. So if you just copy and paste the code, if you just recreate this table here and you slot it into an Excel spreadsheet such as this, then you should be able to recreate these calculations, okay? And I've given it to you in an Excel spreadsheet format because we're going to calculate this in R. I just wanted to provide an additional format in case some of you were more comfortable with spreadsheet thinking rather than hacking it out in R. And therefore you've got multiple different ways to kind of get your head around how we calculate this particular test statistic. Okay, so if you recreate this here, I've put this essentially in here as text, but this represents the formula that's generating this particular cell, so C6. And then also this formula here is the text basically for the formula that generates this particular cell C8. So I hope that you'll be able to just recreate that and have a think about how these different test statistics are created. Okay, so I think that's good. We spent a nice amount of time going over that first example. If it's not clear to you, then have a look in the book, rewatch the video, make sure you try the lab, and hopefully by the time we've gone over that and you've had the spreadsheet example, then it's going to be more clear in your head, which you'll need to have a decent understanding of for the assignment that's going to be set and the end of term exam. So the question is, well, what if my data don't conform to the assumptions? And if that's the case, then well done for thinking about the assumptions. That's really good. That's what I want you to think when you start thinking, well, which test should I use? Are my data normally distributed? What are the types of data variables that I've got? Are they continuous, so interval or ratio, or are they ordinal, for example? This is the type of question that you need to be asking yourself. So hopefully that provides you with a little bit of summary. If we still have two sample difference of means tests that we're conducting, and we don't conform to the assumptions, then we have these other options that we're able to explore. So I mentioned before the Wilcoxon rank sum test is one of the most widely used, and we've also spoken just briefly about the Mann-Whitney U test. So we're going to focus on the former today, the Wilcoxon rank sum test, and we're going to have a look at how we calculate this. We're going to go over an example, and then we'll actually work that out in the lab. So what are we doing here? Well, it's the same as the previous example that we went over, but this is obviously just for non-parametric cases. So before we had the mean of continuous data for each of the samples, but here we have the rank sums of independent samples that may be ordinal, for example. So ordered data. So hopefully you know what I mean by saying that, and if it's not, then just bear with me, and hopefully by the time we've gone over this, it'll be a little bit more clear. So we need to have 2 independent random samples for this to be appropriate. Populations essentially have the same non-parametric distribution, so this is an assumption here, in order to meet the test requirements. And as I said before, this has to be ordinal data. So you could transform ratio and interval data and put it in ordinal form if you want to, or it could just be that you've ended up with a set of data that was already in ordinal categories, which is quite probable, particularly if you're taking surveys, for example. Then you might just inherit survey data from someone else, and this already be pre-categorized, and therefore you're not able to break it down into continuous data. Generally, I feel a little bit uncomfortable about downgrading continuous data into ordinal data because there's a loss of information there. But let's just assume, for example, that we've inherited this data and it's ordinal already, so we don't have access to the underlying continuous data. So then we have different hypotheses. So the null hypothesis is that there's no difference in the rank sums between the 2 different populations. The alternative hypothesis is that there is a difference in the rank sums between the 2 populations, but we're not saying whether it's larger or smaller, so it's two-tailed. Or the alternative hypothesis, which is directional, is whether the rank sums are either larger or smaller than those of the other population. So we specifically say which way we think the effect is going to be. Maybe we think one is larger than the other, and we explicitly state that at the beginning. And we're going to produce a test statistic Z in this case. So how do we calculate that? Well, this is the math equation up here that enables us to get that test statistic of ZW. So WI is the sum of the ranks for the sample I. So bear with me, we're going to cover how we do this. W bar I is the mean ranks of WI, so that's how we get the numerator. And then we have the standard deviation of W, just here, SW, as the denominator, and that's what we need to find. So how do we do that? Well, to get W bar I, we need to basically use this this equation just here. So we need to take the number of entities in the sample which we have for this particular grouping, and we need to multiply it by n1 plus n2 plus 1 divided by 2. And that's how we get this particular metric that goes into the numerator calculation. And then for the denominator down here, we just need to follow through this particular equation. So we'll cover this in the lab, and we'll do it manually. So what are the steps? So this is the bit that you need to pay attention to, because I appreciate before you might not understand what the ranking means, whereas here we explicitly state how you undertake this test. So if you've got 2 individual samples, the first thing you need to do is you need to combine all of the data into a single sample. Okay, so it's a single data set. And it can be listed, you can have a column which says whether it's sample A or sample B. Then you have a variable which states all of the metrics that you're interested in. You then need to order and rank that whole data set from smallest to largest, okay? And when you have values that are tied for a particular rank, then the average rank value is assigned to each position. You then need to sum all of those ranks based on whether it's sample 1 or sample 2 or sample A or sample B respectively, and that provides the sums for the W values, okay? So you see here where we have the WI, we get that by summing these particular the particular rank values. That then allows us to obtain the ZW, so the test statistic. And then we can get the p value from this ZW test statistic from a Z table, for example, and then we're able to make a decision, just like we would for any other statistical test that we've already covered, where we've gone through that hypothesis testing approach. Here we just use a p-value because it's swifter. Okay, so let's go through an example. Let's, for example, ask whether the involvement of females in the labour force varies by the economic level of the country. So it's quite similar. It's essentially the same question as the previous one that we went over. But let's just assume that we only have ordinal data to do that. So let's say that we have lower income over here. We've got the number of samples, and we've got the rank sum for this particular group of countries. And then for higher income groups, we've also got the number of samples. So there was 30 before for the lower income, and there's 14 for the higher income. And then we're going to get the rank sum of the sample for higher income, which we've got here as W2. And when we've got this, we're able to calculate the metrics of interest. So what we want to get is this ZW value down here using this equation. First, we need to get the numerator, so we need to get the W bar. So essentially, we crunch through the numbers here, and when we input these numbers into the equation, we end up with 315 as the W bar for sample 2. We need to get the SW value, so that's the standard deviation of W. So down here, we need to basically take the square root of this equation. And when we do that, we get 39.69. And then once we're able to take those data, basically, so we've got the 39.69 as the denominator, we've got the 315 as the W bar 2 over here, 315. And then we're able to input the W2 value just here, which is the sum of the ranks. And then when we do that, we end up with minus 1.805, which provides us with a p-value of 0.071. Okay, given the fact that this is obviously two-tailed because we didn't say which way we thought the level of involvement would vary. Okay, so hopefully that provides you with enough information for how we make that. Obviously here we don't reject the null hypothesis because we don't have enough information. We don't have enough confidence to do that. It's not below the level of confidence that we need. Okay, so let's move on. So if before we were focusing on non-parametric two-sample difference of means, then here we're going to focus on non-parametric two-sample difference of proportions. And I'm not going to spend long doing this. I just want to draw your attention to it because we will just provide a quick example within the lab. So we want to compare the two independent sample proportions based on differences. So the requirements here are that the random samples are independent and that the variables are binary, essentially. Hypothesis. So we've been through this before. So the null hypothesis is that the proportions from the two samples are essentially equal and not significantly different, whereas the alternative hypothesis is that they are significantly different. And the test statistic that we want to achieve is ZP. And essentially we can get that by taking the difference of proportions between the two samples and dividing it by the standard error of the difference of the proportions. And we use these equations down here. I'm not going to provide a written example now. We're going to go over it in the lab. Hopefully this is starting to become clearer to you now. We just need to make sure that we have the correct values to input into P1, P2, for example. So let's move on to the matched pairs tests now for dependent samples. So the following two tests represent the dependent sample tests. It means that the observations are essentially the same entities that have been sampled twice, which makes them a pair, a matched pair. So this is done, as I say, by repeating sampling potentially at different times, so before or after an intervention. So home values in a neighbourhood before or after new tax laws are passed, or farm productivity before and after a new management practice is introduced, maybe use a different type of fertiliser, for example. So the matched pairs t-test, what we want to do is compare for the difference between these two samples for matched entities. The requirements are that essentially we have a random sample, that we have paired data for xi and xy, so data collected for 2 different points or 2 different samples before or after. But they're dependent, so they're matched. The populations have to be normally distributed, so Gaussian, they have to have a bell-shaped curve in their distribution, and the data has to be interval or ratio based, so continuous. The hypothesis, so we have the null hypothesis that delta is the same, so the mean for the sample is the same as the population, essentially. Whereas the alternative hypothesis is that the delta value, so the mean, is significantly different from the population. And then we also have the directional hypotheses as well. The point is that we want to obtain the test statistic TMP. So to do that, we basically need to take the numerator, so d bar, and we need to divide it by this value down here, so sigma d. So essentially the numerator is the mean of the matched pairs, so we know how to do this. We know how to obtain the arithmetic mean because we've done that before. So in this case, what we do is we get the differences for each pair, so that's di, so we subtract yi from xi, and that gives us the difference. And then what we need to do is we need to sum all of those differences up, so sigma di, and then we need to divide by the number of entities in the sample, and that gives us the mean of the matched pairs differences. So that's the numerator. And then for the denominator, what we need to get is the standard error. So basically, we are getting the standard deviation of the matched pairs differences here, and then we're dividing it by n times the number of degrees of freedom and taking the square root. And that's how we get that denominator. So then we're able to get the test statistic and actually see whether we think that there's a significant difference for the samples that we've taken. So let's look at a question. Does the historical temperature data set show an increasing trend? So what we're saying here is that it's a directional hypothesis. We think that there's an increasing trend, so we're going to want to be looking in the upper part of the distribution. We've got the data just pasted in here. So essentially we have the average annual temperature data for weather stations in the American Corn Belt. We're intending on using the matched pairs test, and this is the name for each one of the weather stations. And then we have the 1974 to 1975 temperature value in Celsius, that's Y. And then we have the 1994 to 1995 temperature here as the X variable. And we've got all the values just stated down here. So we have sample point 1, Y, and we have the second sample point, which is about 20 years later, here as X. And then we're able to get the D value. So you'll remember that we needed to get that just here, the difference for the matched pairs. Essentially, we need to subtract Y from X. And that gives us the magnitude of the differences between those 2 data points. And that's what this column is doing here. And then we're able to allocate a particular rank to those different data entry points. So what does that mean in terms of calculating the statistics that we want? Well, we need to get the sum of D, we need to get the variance of D, we need to get the number of total sample points that we have. We need to get the mean value of X, so X bar, and the mean value of Y, Y bar. And essentially then we're able to run through those equations that we have for this particular statistical test. So the test statistic down here, TMP, needs D bar divided by sigma D. So essentially we need to get the numerator, which is 1.96, which we calculate just here. I hope that's clear to you. So we've taken the sum of D divided by the number of data points in the sample, 28, and we get 0.196. And then we're able to essentially get SD over here by running through the equation that I posted up in the bottom right-hand corner of the previous slide. So we're able to get 0.501 here. So that's essentially the standard error of the mean difference. Okay, and then essentially we're able to get the test statistic, which is 2.07. Which is, it's quite large. Obviously, given the level of significance that we specify, which is, we're looking for a p-value below 0.05, so we can be 95% certain. The p-value which yields here, given 27 degrees of freedom, is 0.027. So that's below 0.05, so we're 95% sure that the results haven't just occurred by random. So essentially, given this information, we can be at 95% certain that we can reject the null hypothesis. Okay, there's enough information here for us to reject the null hypothesis.